I was so good for the first couple of months. Okay, I've now started the recording. Thank you for shouting at me. All right, so last day and the day before, I guess I've been talking about lambda calculus and how it is a complete model of computation. And I'm trying to convince you of that by showing you that anything you can do in Racket, you can do in the lambda calculus. I introduced Booleans and I introduced functions. And I introduced lists. And just at the end of last day's lecture, I foreshadowed how we're going to deal with recursion in the lambda calculus. So we'll pick up talking about recursion, and then I'll talk a little bit about how we're going to implement numbers. And hopefully you can use your imagination to convince yourself that if you have Booleans and functions and lists and recursive functions and numbers, that you can actually use the lambda calculus to write any program of your choosing. You can always translate. Sure, we don't have characters, but you can translate characters into numbers using Unicode and so on and so forth. Those are just bells and whistles. All right, so recursion. Let me just start off with talking about define here. So in Racket, you've got this define clause. In student Rackets, you can only use define in the definitions window. In the full Racket, you can use define in other places, but the basic idea is the same. You've got some expression and you bind a name X to that expression, and then you can use that in one or more subsequent expressions. So E1, the value of E1 is bound to X. And then whenever you use X inside E2, it means whatever that expression is. Okay, so I'm going to deal with this in two different ways. First of all, I'm going to consider the case where X is not mentioned, is not free in E1, right? So that's just your normal define X, plus 1, 2, 3. There's no X defined, there's no X in the expression, and therefore this is not a recursive definition of X. And if you want to do something like this, it's easily done with a lambda. You take E1, you parameterize it by X using a lambda, and then you apply that to E2. And in mathematical notation, this is sometimes it can be read as let X equals E1 in some expression. Okay. That's the forward way of looking at it. I'm sorry, let X equals E2 in some expression. Or you can say E1 where X equals E2. Well, these are common notations, but those are the same thing. And then this notation is basically this one, where we say we define X to be equal to E1. And we substitute E2 for X. Actually, this should be let X equal E1 in E2. I guess I should be consistent here. Define X to be E1 means that the result is E2 and X is defined to be E1. Okay, this says that the result is E2, where X is defined to be E1. I apologize for the mess. And now we can say let X equal E1 in E2, or we can say E2, where X equals E1. Yeah, I should not switch notations in midstream, otherwise I confuse myself and you. I apologize for having done that. Okay. So let is allowed in the student languages, at least with lambda and up. define can be used anywhere in the full languages. Okay, so that's the non-recursive case. What about the recursive case? Here we have a case where F is defined, is to be the result of E1, but obviously writing this out in advance didn't do me any good. But F is in the free variables of E1. So E1 is a recursive definition. Okay, so how are we going to deal with that? Well, what we're going to do is we're going to take F, we're going to take E1, and we're going to parameterize it by F. Okay, so all we do is exactly the same E1, the body of our function, but instead of saying define F, we're going to say lambda F. And then we're going to use this magical, mystical Y combinator in order to convert this into a recursive function, which is equivalent to this. And then in E2, we can use that as we did before. Okay. So basically, all we need to do in order to create a recursive function is stick a lambda in front of it and then stick Y in front of it. And Y is defined like this. Kind of a messy function, but it's parameterized by F, which is our function. And what it does is it takes this lambda function, which is lambda s dot f of ss, and applies it to itself. Okay, so basically what this does is this creates a new function that then passes to itself as a parameter to itself, just as we did last day. And in doing that, what it allows you to do is, if F is a curried function, what it does is it makes the first parameter to F a copy of itself. So F is passed a copy of itself as its first parameter, and then whatever other parameters it might have later on. And the nice thing about being passed a copy of itself is it can then use that copy, it can apply that copy and get the equivalent of recursion. So in order to use Y, basically, in order to use the Y combinator, all we have to do is that. Now, supposing, we have a very simple recursion here, where we're going to define F to be a lambda function, and all it does is a recursive G of F of X. Well, there's our G of F of X, lambda X, G of F of X. That's exactly the same as there. But all we do is, instead of define F, we say lambda F, and then we apply Y to the whole thing. This gives us our recursive function. All right. I will go back, and when we revisit the Racket code, we'll take a little bit more time to look at the derivation of this. There are a million other websites and so on that will play with your mind and attempt to explain why better. But the idea is basically exactly as I introduced last day, that what we're doing is, instead of the recursive function that we're trying to define F, we actually define a helper function that has itself as its first parameter. And then once you apply it to itself, then the result is F. Okay. So that's recursion. At least this is the cookbook for recursion. What about numbers? Oh, I saw a chat that said, how will the recursion stop? Well, that particular example was a oversimplified example that was infinitely recursive. And if you write an expression that doesn't terminate using recursion, it will not terminate whether you do it in lambda calculus or whether you do it in Racket. If you wanted a more complicated example, instead of just saying g of f of x, say if something or other, then g of f of x, otherwise do something that isn't recursive. Like you have to add a non-recursive case or else the recursion is not going to terminate. Okay, so natural numbers. We're going to talk about natural numbers. Now, the world has changed since I went to school. When I went to school, my teachers all told me that natural numbers were the counting numbers starting with 1, 1, 2, 3, 4, 5, and that whole numbers were the non-negative integers, 0, 1, 2, 3, 4, 5. Somewhere along the line, somebody decided that they would call natural numbers the numbers starting with 0. And that definition has pretty much taken hold, but be cautious if you're reading stuff. When you see natural numbers, it's not necessarily as clear as what we think. That said, programming language people tend to say natural numbers are the non-negative integers. Okay, so we need a way of representing 0, 1, 2, 3, 4, 5, 6, 7, and so on up to infinite. I'm going to discuss very briefly 3 different ways to do this. Number 1 is church numerals. This is perhaps one of the first ways that numbers were represented, and they use very weird nested functions. If you think the way that I represented lists and empty and so on was bizarre, church numerals are even more bizarre. We are not going to go into the details of church numerals in this course. There's a reasonably succinct explanation on the web, but basically they're built like car and coulter, where you poke at them, and you can do add 1 and subtract 1 and 0, and that lets you implement the integers, right? If you the natural numbers, if you've got add 1 and subtract 1 and 0, then you can build other arithmetic operations using those primitives. Okay. Since we've already defined cons and car and coulter and lists and booleans, we're, instead of using church numerals, going to look at using lists to represent numbers. And the simplest way to use a list to represent a number is just to have a list where the number that it represents is the length of the list. So if we have a list with 0 elements, that represents 0. If we have a list with 1 element, it represents 1. Now, what's the value of those elements going to be? It doesn't really matter. For this explanation, I'm just going to make it a list of trues. Okay, so 0 is going to be implemented by the list empty. N, where n is greater than 0, is just formed by consing true onto whatever the representation is for n minus 1. So, for example, 3 would be represented as true, true, true. 0 would be just the empty list, and so on and so forth. So add 1 is really easy to do. You have a number represented by a list of length n minus n. You can build the number n minus 1 just by consing true onto that list. You make it 1 longer, and therefore it represents a bigger number. Subtracting 1, you just take the coulter. Make the list 1 shorter. 0, Well, it's 0 if the list is empty. So this is an exceptionally simple, well, once you've figured out lists and recursion and so on and so forth, way to implement numbers. How are we going to add numbers? Well, if you want to add 2 numbers n and m, and you happen to know that m is equal to 0, that's an easy trivial case. That's just the number n. What if m is greater than 0? Well, what we can do is we can subtract 1 from m, add that to n, and then add 1 to the result. So again, our invariant is that n and m are going to sum to the same thing. But what we'll say is we're going to subtract 1 from m, add 1 to the result, and the overall result is going to be the same. So there we go. Multiplication can be done in much the same way. If we want n times m, in the trivial case that m is equal to 0, the result is 0. Anything times 0 is 0. If m is greater than or equal to 1, well, then what we do is we take n times 1 smaller and add another n onto it. So we add n to 0 m times in order to do n times m. I will leave it to your imagination for how to do subtract and divide and exponentiation and all that kind of stuff. You can, again, come up with reasonably simple rules. Now, unary naturals are sufficient for me to prove that I can implement naturals using the lambda calculus, but they're not quite enough for me to, they're not great for running time. So if you, for example, have two numbers n and m, and you want to add them, this is going to have to do m operations. So it's going to take O of m time. If you want n times m, well, it's going to take O of m additions, and each addition is going to take O of m time. And so it ends up being O of m squared time. So the running time for unary, or for doing computations on unary lists representation of natural numbers, is fairly atrocious. All right. What about binary natural numbers? So binary natural numbers are also going to be represented by lists of true, by lists, but they're going to be lists of true and falses. And this is going to be a positional number system. We're all used to base 10 positional number system, where the rightmost digit indicates the units, and the next digit indicates the tens, and the next digit indicates the hundreds, and so on. So in general, you have powers of 10 that each digit represents. In binary, we only have two digits, 0 and 1. And again, the first digit represents units, which can be 0 or 1. The next digit represents twos. The next represents fours. And in general, each digit represents twice as much as the previous digit. The other thing we're going to do is, since we generally write lists from in a particular order, we're going to write our binary numbers starting with the digits as the first element of the list. So the normal way we write out lists means we're going to write these numbers backwards. We'll start with the units, we'll then go to the twos and the fours and so on. Anyway, let me give a recursive definition of this and then some examples. So we're going to represent the number 0 as empty, same as we did for unary. If we have any number that is greater than 0, we can double that number by sticking false at the beginning of its representation. And if we have any number at all, we can double it and add 1 by sticking true at the beginning of the representation. So let's look at a few of these things. So 0 is represented by empty. 1 is represented by true. 2 is represented, well, you get 2 by doubling 1. So doubling sticks false there. So 2 is false, true. 3 you get by doubling 1 and adding 1. So you get true, true. 4 you get by doubling 2 and adding, by doubling 2 and sticking false at the beginning. So you get false, false, true. Now it's kind of annoying to write false and false, true all the time. As a shorthand, I'm going to use the digit 1 to represent true and the digit 0 to represent false. So 0 is still going to be null, an empty list. 1 is going to be just a list containing 1. 2 is going to be 0, 1. 3 is going to be 1, 1. 4 is going to be 0, 0, 1, and so on and so forth. So, and 5, if we're going to do it, is going to be 1, 0, 1. So this means that there's 1 in the units. This means that there are 0 2s and 1 4. So 1 1 and 1 4 totals 5. So this is the basic representation we're going to use for numbers. Okay. Notice that except for the case of 0, all of these representations always end in a 1. And that's not a coincidence. Okay. So we never have binary natural numbers that end with a false as the last element of the list. Okay. How are we going to implement stuff using binary natural numbers? Well, 0, huh? Is just the same thing as empty, huh? And as a couple of helper functions, I'm going to implement, or I'm going to show you how to define odd and even. Odd, huh, for 0. Odd, huh, of 0 is going to be false. So 0 is not an odd number. If the number is not 0, we know that it's odd if the first digit in its representation is true. So odd, huh, is just the car of the number, provided the number is non-zero. If the number is 0, it doesn't have a car. Even, huh, is just the opposite of odd. So if odd is true, even is false, otherwise it's true. If I had defined not, I could have just said not odd, huh, of n was equivalent to even, huh, of n. So now I can test whether a number is even or odd or 0. Well, I guess to put this in a lot more logical order, I can first determine whether a number is 0 or not. And if it is not 0, I can then determine, whether it's even or odd. Okay, so let's look at a few things we can do with numbers. Add 1 to 0 is clearly 1. And that's cons true of empty. Add 1 to n. Well, if n is even, it's easy to add 1 to it. Let me go back to my previous example. 4 is even. All I do to get from 4 to 5 is change the first element from a 0 to a 1. 2 is even. All I do to get from 2 to 3 is I change the 0 to a 1. 0 is even, but it's a little bit different. So add 1 of 0 is just 1. Add 1 of an even number, I stick cons, I stick a 1 onto the beginning of the number and I remove the 0 that was there before. What if it's odd? Well, if it's odd, I'm going to do something that's a little bit odd. Well, a little bit strange, I should say. I'm going to take the cutter of the number. So I'm going to ignore the first digit. I'm going to add 1 to effectively the 2's column of this number. So this is going to, in effect, add 1 to the remaining number. Well, it's going to take the remaining number, divide it by 2, add 1, but then when I stick a false on there, I'm going to multiply it by 2 again. So, I'm going to subtract 1 from it. So basically what I'm doing here in a really roundabout way is I'm taking half the number, I'm doubling it, excuse me. I'm adding 2 to the number and then I'm subtracting 1 back from it, okay? So I'm adding 1 to half the number, doubling it and subtracting 1. Sub 1 and is much the same thing. Sub 1, subtracting 1 from a number is easy if the number is odd. And again, if we go back, subtracting 1 from 5 is easy. you switch the 1 to a 0. Subtracting 1 from 3 is easy. You switch the 1 to a 0. And so what we do here, if it's odd, we're just going to change it from true to false. What if it's even and greater than 0? If it's even and greater than 0, then we do the same trick. Basically, we subtract 2 by subtracting 1 at the 2's position, and we add 1, so that the net effect is that we've only subtracted 1 from the number. So these are the basic operations on binary natural numbers. What about addition? Well, if we want to add a natural, okay, start with, we can do addition and subtraction exactly the same way we did it for we can do addition and multiplication the same way we did it for natural numbers. The way we did it for natural numbers only depended on add 1 and sub 1 and 0, huh? So we can do that. But there's a more efficient way to do it, which is, well, to start with, we have to realize that if we're adding 0, we don't have to do anything. But if we're going to add n and m, okay, we're going to have two cases here. If m is even, if we add two numbers, and we know that one of them is 0 in the ones column, we know that the ones column then will be equal to whatever the ones column was in the other number. So that's that. And then we know that the rest of the number can be derived just from adding the two critters. Okay, we take the 2 digits along and so on up, and we add the critters. What if m is odd? Well, we can do the same sort of trick we did before. If m is odd, we can make it even by subtracting 1 from it. And then we can do our addition because I've made it even. And then I can add 1. So we take away 1, do the addition, put the 1 back, and we've now done our addition. Okay. What about times? Well, once again, we can do times by the same way as unary, but it turns out we can do better than that. We can do a version of times that takes O of log m times log n steps. And the way we're going to do this is like good old-fashioned long multiplication. Remember how you did long multiplication in school? You have some number x times some number y. You multiply this y by these x's and you get some answer. And then you multiply that y by that and you get some other answer. You multiply that by that and you get some other answer. And then you add them all up. How many operations does this take? Well, it takes the length of the number of y's times the number of x's in order to do this. Well, the number of y's, I guess I didn't prove this, but it's pretty easy to show. To represent the number n in binary requires a list of length log n. To implement m in binary takes a list of length log m. So if we wanted to multiply n by m in binary, the total number of operations is the log of m times the log of n. Okay, so if you can figure out a way to do this, elementary school long multiplication, you can make it work in log m times log n number of steps. It turns out you can do better than that. Long time ago, a guy named Karatsuba figured out that you could do multiplication in log m plus log n to the k, where k is less than 2. See, if you had log m plus log n squared, that would be no better than that. But log m plus log n to the k, where k is less than 2, does give you an advantage over this. In assignment 9, you have the opportunity to try your hand at implementing this algorithm for 1/3 of the marks for one of the questions. I do not expect everyone to do this, but if you want full marks in the test or in this assignment, you need to be able to come up with an implementation that is faster than this. Again, I hope some of you have fun doing this. I know some of you might not have fun doing it. If you don't have fun doing it, don't do it. It's not going to cost you enough marks that you'll ever notice it in your final grade. But if you are driven for perfection, figure out how to do it. Now, it turns out you can do even better than that. You can do log m plus log n times log of log m plus log n. And you can do this using a thing called the fast Fourier transform. Well, if you've talked to engineers, they think fast Fourier transforms always work in exact numbers, but you can do a thing called the discrete fast Fourier transform that works with modular arithmetic. I assume in CS1X5, you've talked lots about modular arithmetic by now. So modulo certain prime numbers, you get a nice field defined. So you got plus and minus and times and divide. And if you implement those all very nicely, you can implement fast Fourier transforms in order to implement very fast from a big O sense multiplication. I doubt that you're going to do this in this course. And even if you try to do it in this course, I doubt it will run any faster than Karatsuba's because it's a pretty complicated algorithm. And while people on the theory side of the tracks like to say all that matters is big O, in practice, if you get a bitter big O, but it's actually 1,000 times slower for anything Marmoset can test, you're not going to get the Marmoset marks. Once upon a time, I spent some time doing number practice, discovering prime numbers and factoring Fermat numbers and stuff like that. And even then, where we were looking at numbers like of the size 2 to the 2 to the 2,000 and things like that, we did not find that Fourier transforms were an advantage. On the other hand, that was about 5,000 years ago. So maybe with modern hardware and so on, they are. But I doubt they are within the context of this assignment. Okay, so that's multiplication. And what I think I'd like to do now is share the screen and go back and revisit our recursive example a little bit. So let's see if I can find share screen. Okay, here we are. And I kind of blasted through this last day. To refresh your memory, I defined true and false and if and car and cons and could've and all this cool stuff. And then I have lists of trues and falses. That's the only thing I can have lists of. Well, I guess I could have lists of other lists, but I have lists of trues and falses, and I wanted to implement AND list such that AND list is false, is true if all of the elements of the list are true, and false if any one of the elements is false. And I first of all defined a recursive form of this. This is not something I can translate directly into lambda calculus. Because, as you can see, inside and list is a free variable. So we can't do that. At least we can't do that trivially. That said, this shows the logic of how and list works. If the list is empty, the result is true. If the car of the list is true, that means you take the and list of the rest. Otherwise, you cut bait. If you ever see a false, the overall result is false. So that's our recursive and list. And I hope I convinced you last day that it works because it shows false for X and true for Y. Because Y is all truths. Okay. And then very briefly introduced and list helper. If we compare and list helper, you see that and list has only one parameter, which is the list. And it recursively invokes itself. And list helper is exactly the same, except it has two parameters, self and list. Okay, that's the only difference. It's got two parameters. So in the definition, I say lambda self list. And then when I come to do the recursive invocation, I don't use and list helper. So this is not, and list helper is not a free variable in this expression, but instead I use self. This first self, this is the actual recursive call to and list helper. This is and list helper, apply the function and list helper, but I'm going to do it by applying this parameter self because I trust whoever invoked this to have passed me a copy of myself. The second parameter, or the second use of self, this is the argument. Self requires self itself as its first argument. And then finally, the second argument here to self is coulter of list, which is what I really wanted to pass to and list in the first place. So and list helper behaves just like and list, except it has an extra parameter called self. So whenever it invokes itself with an extra parameter called self. And when we use it, to build and list one, all we do is apply and list helper to and list helper and the list. So and list one should behave the same way as and list. And it does. And there's no recursion. Okay. Let me now introduce just a slightly reformatted version of and list helper. First of all, I'm going to write a curried version of and list helper. Okay. So here is and list helper. That's what we just used. And curry helper is exactly the same, except as you recall from last day, there are two ways of writing a function that has more than one parameter. The uncurried form is what Racket typically uses, but you can also curry the function. So and list helper is a lambda with two functions, self and list. Whereas and curry helper is just a function with parameter self, and then the result of that function is a lambda with parameter list. So this is just the curried form of exactly the same function. when we use the curried form, rather than saying self of list, we say self of right here, okay? Sorry, rather than saying self of self, we say self coulter of list with no parentheses. We say first self of self in brackets for application, and then coulter of list. So and curry helper works exactly the same way as and list helper, only we're going to use it a little bit differently. Now, instead of saying and list curry of list and then having a lambda that applies and curry helper and curry helper and list, all we need to do is apply and list curry to itself. And this gives us a version of and list. I didn't mean to change anything in the definition undo, but I'll redo it just to prove that I didn't. Okay. So once I have done that, you see that and list curry, all it does is apply and curry helper to itself. And curry helper is not recursive. So given that it's not recursive, I don't actually need to define a function. I can just substitute in the definition of and curry helper twice, once here and once there. So and the difference between and list curry and curry no helper is that I have done the substitution myself. I have applied and curry helper to and curry helper, and I'm going to substitute in the definition. There you go. Okay. So we get lambda self, lambda list, if empty list, blah, 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 blah. And it turns out that and curry helper of X gives me false, and curry helper of Y gives me true. So I have now written an completely non-recursive expression that does this recursive operation of going through the list. Okay, let me do one more thing. And that is, rather than making this and curry helper specific to doing and list, which is what all this stuff does, car of list and so on, I want to abstract that out. And I'm going to abstract that out by calling the recursive, the function that I want to make recursive, I'm going to call it F. And this, when I want to make this function recursive, the first thing I do is I curry it by adding another parameter, self, and then I apply F to self of self. And here's how I can use my generic curry, no helper. All I have to do is take generic curry no helper, and I pass it a new function, which is parameterized by itself, lambda of and list. And notice that lambda of and list uses AND list. It doesn't use AND list of AND list or self of self or whatever. It just uses AND list. And magically and mysteriously, it works. So all this does, the only difference between AND curry no helper and generic curry no helper is that I've taken all of the logic that calculates AND list and I've moved it into a function called F. And then I can just pass an appropriate version of F when I need to. Okay, so that's my development of recursion. Let me go to another screen here.
Professor, there's some more recent hands.
Yes.
Professor, I didn't understand the curry no helper function. Could you explain that again?
Okay. Where did I go here? So I have AND list curry. All AND list curry does is it applies AND curry helper to itself. All I do to get from AND list curry to AND curry no helper is for each place of AND curry helper, I just substitute in the definition of AND curry helper. See this? Oops.
Oh, I understand.
I've just manually done the substitution myself of the definition of AND curry helper, and I put it in twice. So I don't need AND curry helper anymore because I've substituted in the equivalent definition. Okay.
Okay, I understand. Thank you so much, sir.
Okay, in assignment 9, you're going to be asked to do a number of things. I guess the first 2 assignments ask you to write, racket expressions to do stuff without using define or numbers or cons or anything that you've come accustomed to. And then the last assignment asks you to do implement some of these arithmetic operations that I've been talking about. To guide you a little bit, we give you can download a copy of this module, which is called lambda.racket. And as you can see, it is a module and it provides all kinds of cool stuff. It provides true, false, if, or, and, not, cons, car, coulder, empty, empty, y, which is the y combinator, capital Z, which is 0, Z, which is the test for Z, add 1, add, true, True, is just like display. It's just going to print out or it's just going to give you a human readable version of whether a function was true or false. Tan converts from a binary natural number in our representation to a racket number, and nat goes in the opposite direction. So true, tan, and nat, those are only used for debugging. They're not going to be used for solving any of the problems in assignment 9. Okay, so these are provided. And we can look briefly at the definitions. The definitions are slightly different from the definitions I gave on the other example, but they're not that much different. To start with, you'll see that true, I use different variable names. Instead of X and Y, I use yes and no. And also this is the curried form of true, right? In the previous example, I used the uncurried form. Doesn't matter so long as you're consistent. False is also the curried form. And true, is just a function that takes a Boolean B that's either true or false. And if it's true, it yields the symbol yes. And if it's false, it yields the symbol no. Don't forget, you're only going to use true, for debugging. You're not going to use true, or for displaying output. You're not going to use true, as part of the implementation of your assignments. If and if is very much the same as we had before, but you do see that the Booleans are all curried, so you have to apply them in the curried function. You do one application to apply the first parameter, and then you take that result and apply it to the second parameter. Or and not are pretty straightforward. A or B is true if A is true, otherwise it's equal to whatever B is. And of A, B, if A is true, then the result is whatever B is, otherwise it's false. And not of A, if A is true, then it's false, otherwise it's true. Cons, again, it has two parameters, car and coulter. For some reason, this is not the curried form, but so true and false are curried, but or and not are not curried. Neither is cons. So it's a lambda with a selector function. And the selector function is applied to the car, and then the result is applied to the coulter. Car is just, you take the pair and apply it to true, and that will give you the car field. Apply it to false, that'll give you the coulter field. Empty is the same as we had before, lambda x true. Empty returns true no matter what you give it. And empty takes what might or might not be a pair. That's LST. And it applies it to this funny function, which is lambda yes, lambda no false. So if this function get used at all, this would be it's going to return false, okay? What happens is empty, if it isn't empty, it gets a true because the lambda is never used. But if it's false, the lambda is applied, and that ends up yielding false. Why we've talked about. Lambda, you'll become best friends with Y soon enough. Z is empty, Z is empty, Add 1. This is more or less an implementation of what I showed on the paper. If X is 0, then we have the result is 1. Otherwise, if the car of X is true, that means if it's odd, we're going to cons false with add 1 to the coulter. Otherwise, we're going to cons true onto the coulter. This is just racket implementation of the rules that I hopefully scribbled correctly on the board. Adds a little bit different from what I said before, because it checks that both, excuse me, it checks two trivial cases. This is probably overkill, but you can work it out for yourself how the add operation works here, because it doesn't rely on an odd or an even. So first of all, it has to check the special cases, and then basically it covers the odd and even cases. So not car of A is saying A. Well, we already know that it's not 0, and if the car of A is not true, that means we know that this is an even number. Otherwise, we check to see if B is an even number. Otherwise, we do this, we add the coulters, and then we add 1 to the result. Okay. Tan and nat, they're just straightforward operations that use the built-in primitives to either to build a number or to create a number. Be very careful. Nat, as you can see, runs in time O of n. If you want to create if you want to see how well your algorithms work on numbers of size 1 trillion, you're not going to be able to use NAT. Maybe you'll have to figure out something cleverer than that for creating your test examples. Tan, on the other hand, I think tan actually works in log n time, so it should be okay. All right. And here there's just a test function that is not exported, but it's used just to test the built-in functions. It builds an addition table for all the numbers between 0 and 5, I think, between 0 and whatever you ask. In this case, it's 5. Okay, so this gives you a skeleton of what you're going to be doing for assignment 9. Questions? Okay, let me go back and just have a parting shot on translating from lambda calculus to racket. So far, we've talked about how to translate racket into lambda calculus and how to translate lambda calculus back into lazy racket. What if we don't want to translate back into lazy racket? What if we want to translate back into good old-fashioned applicative order racket? Well, it turns out we can do that. And we can do that. We can do that by making the following observation. Basically, what we can do is we can build promises wherever we need to build promises. And it all hinges on this particular observation. Let's suppose we have f, and we know that f is a function. Supposing we build a new function, lambda x dot f of x. Remember, everything in racket is curried, or everything in lambda calculus is curried. So if f is a function, we know it has exactly one parameter. Well, this is another function that has exactly one parameter. Well, let's suppose f of foo yields the result bar. Well, if that's the case, if we take this lambda expression and reduce it to by applying it to bar, we get f of bar. So applying f to any argument is going to give us exactly the same result as applying lambda x dot f of x to the same argument. It's not going to make any difference. These are said to be eta equivalent, and pardon my Greek, that funny looking symbol is an eta. And so we say that if we have a function f, that f and lambda x dot f of x are eta equivalent. That means they're going to behave exactly the same way when they're applied. So provided we don't care what's inside, as long as they behave the same way, that's cool. So let's have a look at what happens. So let's suppose that we have a lambda expression E1, E2, where we know that E2 is a function. This can be eta converted to E1 lambda x dot E2 of x. And guess what? Even in applicative order, this is going to get substituted. So this actually builds, we're going to use eta conversion to build a promise. So let's suppose, for example, we have if Boolean A, then B, right? Where these are actually expressions. Basically, if we're just going to pass A and B to these things, that we may need to evaluate these. So let's say we have if of B. Oh, oops, C. If of B, A, C. This is what our if is going to end up looking like. And if these happen to be red X's, instead of that, I can write lambda x dot E1, lambda x E1 of x, lambda x dot E2 of x, and lambda x dot E3 of x. So basically, if I'm doing this reverse translation, what I'm going to do is I'm always going to put in a promise whenever I know that I'm passing a function as a parameter. And it turns out it turns out that you can actually rewrite even y, because the trouble with y is it ends up with this thing self of self. Well, that might be a problem, but you can always rewrite self of self as lambda x dot self of x applied to lambda x dot self x, and that will defer evaluating these things. Okay, I mean, this one is not really essential, but anyway, so if you want to look more at this, you can look for the applicative order Y Combinator. Okay. So the applicative order Y Combinator is something you could do. Now, we're not going to do this in this class. So it's for your information that you can do eta conversion in order to build promises. I am not going to ask you to translate any things that work in from lambda calculus into the equivalent non-lazy racket. I am going to ask you to translate from lambda calculus into lazy racket, but translating into non-lazy racket, the only takeaway I want you to take from that is that it is possible to do it when you have chosen representations for your values that are functions. Because whenever you have a value that you know is a function, you can always wrap a lambda x around it and thus make it into a promise and thus defer its evaluation until later. You get, in effect, normal order evaluation. You're not going to get lazy evaluation, because if you substitute the same eta converted function in 10 different places, it will be reevaluated. Or at least it will, if needed, it will be reevaluated in each of those 10 different places. Okay, I believe that we've covered all the nuts and bolts for assignment 9. For assignment, excuse me, not for assignment 9, for assignment 10. Go back and rewind my lecture, and whenever I said assignment 9, think assignment 10. Assignment 9 involves streams, but no lazy. Assignment 10 involves lazy. It involves translating lambda calculus to lazy racket, and it also involves doing arithmetic in lazy racket without using any built-ins. So that's assignment 11. Sorry, assignment 10. I need to learn how to count. For the exam, you're only responsible for the material up to assignment 8, which you've already completed. I will make a practice exam available as soon as I can. I'm sorry it's not out yet. It will be essentially the same as for the first midterm. The only difference, as I say, is that I may be asking you to submit multiple files instead of submitting just one file, which contains your answers to all problems. Okay, any questions or complaints?
Hello, Professor. A student has been asking about whether there's any things you recommend for practicing the midterm, like outside of past papers and redoing the homework.
Past papers and redoing the homework is about all I can think of. I mean, you can go through the lectures and try to reproduce the examples that are given in the lectures as well. For basic stuff on trees, I mean, it's pretty, you can seek out generic references on trees and the definition of big O and how to use modules and stuff. But no, I think if you do past exams, I recommend doing past exams cold. There's no point trying to memorize the answers to past exams. But once you think you have the concepts, go try and do the past exams. And if you feel that you're comfortable with how they work, that's great. If you're not comfortable how they work, memorizing the answers isn't going to help you very much because you're unlikely to see precisely the same questions on this exam. Matt. Matt, you have a question?
Yeah, hi. I was just wondering, for the exam when we submit multiple files, are we going to have like multiple places to submit it, or do you want it to like zip it, or like how are we going to submit all the files at once?
That's a good question. The easiest thing for me would be to force you to zip it, but you haven't zipped anything. You need to zip files together for assignment 9, but you haven't practiced that. So I'm going to spend the next hour or two trying to figure out what the most convenient for you will be. I will probably have a separate Marmoset submission for each question that requires a separate file. So, you'll have submit Q1, submit Q2, something like that.
Okay, thank you.
No problem. Okay. Go ahead.
Professor, I have a quick question. Can you give example of a lambda calculus function that will make y combinate or terminate?
Sorry, that will make y.
The y combinator terminate.
Well, the y combinator is applied to a function, and so whether the result terminates or not depends entirely on the function.
Yeah, I'm asking, can you give example of a function for which it terminates?
Well, I gave a version I gave a function in Racket here for and list, or for so and generic is an example of a function that applies the y combinator and terminates. I didn't translate that into lambda calculus because it gets large and complicated, but you could certainly translate and generic of x or and generic of y into lambda calculus using the steps that I've mentioned, and that would give you something that terminates. Did I answer your question?
Yeah, yes, sir. Thank you.
No problem. Jessica.
Since when we're looking at the questions, we don't get to really check our submissions. Do you have any general tips for how to approach exam questions so that you make sure you don't like overdo the runtime or the CPU limit?
Test your questions, obviously. If there are runtime constraints that are exceptional, they'll be stated in the exam. But in general, for the material that we've covered, for example, if you have to insert into a binary tree, you would expect that you would have to do the kind of normal best practice implementation of that. And if you did something worse than that, it may run out of time. So I'm sorry, this is kind of a vague answer. There's not, we will try to avoid having questions where you simply have to guess at what the running time is supposed to be. Going back to assignment 1 or midterm 1, I know some people were a little bit confused by runtime, but we were, yeah. We'll try to be more specific than we were on assignment 1, okay? Or on midterm 1.
Okay, thank you.
Andrew.
Hi, I'm just wondering if there are any solutions to the past papers that were uploaded on Piazza.
No, but you're welcome to discuss them on Piazza, and the ISAs may or may not give some hints, or your colleagues might give some hints or something like that. But no, we don't have we don't have canned model solutions, partly because we're too lazy, but also partly because we want to discourage you from trying to memorize the answers.
Okay, thank you.
Ariam?
Professor, since the time zones have changed, would it be possible for you to release the papers 1 hour earlier so that it's still like the same time as the last midterm?
Remind me when I released it last time, 9:30?
Like
Or was it
it's
10?
I think you released it at the same time, but then since the Canadian clock has gone 1 hour behind.
Sure,
So
I can give an extra hour. I can, so I'll release it. It'll still be due at 10 Eastern Standard Time, but I will make it available at 9 Eastern Standard Time.
Okay, thank you so much, Professor.
No problem. Matt?
Sorry, I just had one last question. There were lots of, or not a lot, but like there was a decent amount of questions on the practice midterm that wanted us to like either find or prove the like the big O. I just like I was wondering how specific or like what format like we should stick to when we're doing these proofs, because like I like it's pretty broad how you can do a big O proof.
There are two kinds of proofs. One is proofs about the running time of your program. For proofs about the running time of your program, you really just have to give us a convincing argument that, for example, if you're trying to do insertion sort, you have to give a convincing argument that, this outer recursion requires n steps, and each step requires O of 1 to do the coulter and O of I to do the insertion, where I is the number of the step, and this is the sum from 1 to n, from I as 1 to n of I, or of I, which is n squared or something like that. Okay, I mean, this is excessively hand waving, but provided you convince me, you assume that the reader understands racket, and that if you make a simple assertion about how many steps racket takes, that they will believe you. Similarly, if the size of the problem is reduced by half each time, we can see that the sum is less than the sum from I equals 1 to infinity of 1 plus a half plus a quarter or so on, which is O of 1, or whatever. Okay, that's hand wavy. So that's number one. About your program, yes, you can just assume that the reader knows what the bits of the program do, and you just have to argue about the principal recursive steps and how many times they happen and what the resulting big O is. For the big O from first principles, basically follow assignment 6, if you want to prove something is O of something else or something else is O of that. I think one of the past midterms had a kind of a nasty question of proof something is that 2 O's are the same. I may not have discussed that this year. Basically, in order to prove that O of A is equal, O of F is equal to O of G, you just prove that F is a member of O of G and that G is a member of O of F. And that shows that they're that they're the same. So, again, in terms of elementary math, be careful, when you're doing substitutions into inequalities, the main thing you have to do is make sure you show the substitutions are correct. And if you multiply both sides of an inequality by the same number, you better make sure that you better prove that number is positive. If you add a certain amount to both sides of the inequality, well, that maintains the inequality, and so on and so forth. Just make sure that you obey the rules for inequalities if you're trying to do something from first principles. I don't think I'm going to ask you to do a lot from first principles on the midterm, but you are responsible for that. You could well get something like one of the problems in assignment 6 to do.
Okay. Yeah, thank you so much.
Excuse me, Professor. Actually, this lambda calculus is something totally new for myself. And how do you recommend for me to practice this translation between the lambda calculus and the lazy racket? Actually, as you said that the normal racket is not necessary for us.
Do assignment 10.
Thank you, sir.
No problem. Matt, are you still, your hand's still up?
Oh, sorry about that.
Oh, okay, so you don't have another question?
No.
Okay, any more questions? All right, I will get to work setting up your midterm, and you get to work studying for it or learning about lambda calculus or whatever. See you next class.